In this video, I will discuss conjugated compounds, molecular orbitals, and UV-Vis spectroscopy. There are three classes of dienes. So first of all, what is a diene? It is a molecule with two double bonds. In accumulated dienes, the pi bonds are adjacent. In a conjugated diene, they are separated by a single bond. Isolated dienes have pi bonds that are separated by more than one single bond. This shows the pi bonds represented as overlapping p orbitals. So in the accumulated diene, the pi bonds are perpendicular. There's no conjugation. In the conjugated diene, all of the pi bonds are overlapping, and this is what makes it conjugated. And in isolated pi bonds, the pi bonds do not overlap with each other. They are separated, and therefore there's no conjugation. Conjugation is important because it gives a molecule extra stability. Heteroatoms may also be involved in a conjugated system. So here you have a pi bond between those two carbons, and you have a pi bond between the carbon and the oxygen. Those pi bonds are in conjugation. Here you have these pi bonds, which are in conjugation with each other, and then this pi bond here is also in conjugation with the pi bond in that carbon-nitrogen double bond. This pi bond is isolated from the other pi bonds. Notice how there's more than one single bond between it and the other pi bonds. The bond lengths in the single bonds that connect a conjugated pi system are shorter than typical single bonds. This is due in part to the overlap of sp2 orbitals that make that sigma bond. So here, these carbons are sp2 hybridized. Therefore, that single bond between them is formed by overlapping sp2 hybrid orbitals. Here, if we look at ethane, these carbons are sp3 hybridized, so that bond between those two carbons is due to the overlap of sp3 orbitals. The trend is that the more s character, the shorter the orbitals and the shorter the sigma bonds will be. So if you have a p orbital, that has 0% s character. If you have an sp3 hybrid orbital, it has 25% s character, and sp2 has a third s character, and sp has 50%, and then of course an s has 100% s character. So I mentioned that conjugation lends stability, and this can be calculated by looking at the heats of hydrogenation. So if we look at this alkene, it is a single double bond. It's not in conjugation with anything else. If we hydrogenate that, so we convert that double bond to a single bond, and we do it for two equivalents, we release 254 kilojoules of energy. In other words, the product is that much more stable than the starting materials. If instead of having two separate double bonds be hydrogenated, we instead use a diene, and we add H2 to that, we release 239 kilojoules of energy. So we release less energy when hydrogenating these two pi bonds when they're in conjugation versus hydrogenating this pi bond in two separate molecules. The difference here is called the stabilization energy. So that conjugation is stabilizing the starting material. There are two stable rotational conformations for butadiene. This is butadiene. It's buta because it's 4 carbons, and diene because it has 2 double bonds. The S-cis conformation and the S-trans conformation. So to convert between those two, you're going to rotate around that single bond. In these conformers, if we have the S-cis, you can see here that the p orbitals are conjugated. With the S-trans, they are also conjugated. So notice how they're all in line and overlapping. P orbitals are only conjugated for butadiene in these two rotamers. In comparing the rotamers, the S-trans is lower in energy because it has less steric hindrance. Molecular orbital theory comes into play when we're dealing with dienes and other conjugated systems. So as a review, molecular orbital theory involves adding atomic orbitals together to form new molecular orbitals. Atomic orbitals belong to the atom, molecular orbitals belong to the molecule, and they extend over the entire molecule. The overlap of p orbitals in ethylene, for example, results in a bonding molecular orbital and an anti-bonding molecular orbital. To determine the molecular orbitals for butadiene, we consider all 4 p orbitals for the pi system. The lowest energy molecular orbital is shown here. That's where all of the p orbitals are in phase and are lined up. The next energetic molecular orbital is shown here, and this is where there would be a node. So when you go from one orbital with one phase to another orbital with a different phase, that's a node. That means there's no bonding happening between those two orbitals. And then the higher energy molecular orbitals are shown here. Now notice that just these two lower energy molecular orbitals are being occupied by electrons. So the 4 pi electrons in butadiene occupy the lowest energy molecular orbitals. Now here there's double bond character between C2 and C3, which is evident by this constructive overlap. However, with the next molecular orbital, there is no overlap between C2 and C3, so there would be no double bond character. Thus, molecular orbital theory explains in an alternate way why that carbon-carbon single bond connecting the two pi bonds is shorter and stronger than a typical carbon-carbon single bond. So we can look at the hybridization argument, but we can also look at molecular orbital theory. Reactions that molecules undergo can often be explained by studying their frontier orbitals, and in particular the HOMO and the LUMO molecular orbitals. HOMO stands for highest occupied molecular orbital, and LUMO stands for lowest unoccupied molecular orbital. And these terms will come into play when I teach you about the Diels-Alder reaction. Conjugated systems absorb in the UV or visible light range of the electromagnetic spectrum. This is the ground state of butadiene, where these are the molecular orbitals. When light is absorbed of a particular frequency, one of those electrons can be promoted to a higher energy molecular orbital, and that would be the excited state of butadiene. In general, the necessary energy to excite an electron from the HOMO to the LUMO falls within the UV or visible region of the spectrum. We can use UV-vis spectroscopy to gain structural information. The amount of light absorbed by a sample is a function of its wavelength and is called absorbance. And so here we would see a particular UV-vis spectrum of butadiene. So this point, that's the peak of the curve, is called lambda max. So that would be the wavelength of light that butadiene absorbs the most. Now consider this question. The absorbance spectrum of 1,3-butadiene, so you may want to draw that out, displays an absorption in the ultraviolet region where the maximum absorption occurs at 217 nanometers. However, the absorption spectrum of 1,2-butadiene does not display a similar absorption. Can you explain this in the chat? In your textbook, the Woodward-Pfizer rules are discussed. I want you to look that up in your textbook and then explain what they are in the chat. The more conjugation something has, the smaller the energy gap between the HOMO and the LUMO, also called the pi and pi star orbitals. The smaller that gap, the greater the lambda max. And remember, frequency is directly related to energy, wavelength is inversely related. So if we are absorbing at a higher wavelength, that means there's a smaller amount of energy. Take a look at these compounds, A, B, and C. I would like you to rank them in order of increasing lambda max, and then explain your ranking, and put this in the chat. There's a special term we use for the group of atoms responsible for absorbing UV-vis light, and that's called the chromophore. Highly conjugated compounds absorb light in the visible region and therefore appear colored. For example, this is lycopene. So notice all of the conjugation here. This is responsible for the red color of tomatoes. Similarly, beta-carotene also has a lot of conjugation, and that's why carrots appear orange. The color observed by your eyes will be the exact opposite of what is required to cause that excitation from the homomolecular orbital to the lumomolecular orbital. So if the molecule absorbs in the red region, we see green. If it absorbs in the blue region, we see orange. I want you to go to Wikipedia and look up an organic pigment. If you go to the link I showed there, there is a list of organic pigments. I would like you to pick one, describe it, and if you can, find out what wavelength of light it absorbs. Conjugated compounds are important in how we have vision. Rods and cones are photosensitive cells in your eyes. In rods, we have a compound called 11-cis retinal. And notice all of these pi bonds in conjugation with each other. That will undergo a reaction with opsin to form rhodopsin. Sources of 11-cis retinal include vitamin A and beta-carotene. You can notice that there is a structural similarity between these three compounds. When the molecule of rhodopsin is excited photochemically, it results in a change in shape, which ends up releasing calcium ions. Calcium ions block channels through which billions of sodium ions generally travel each second. As a result of a decreasing sodium ion flow, a nerve impulse is generated, and that is interpreted as visual information. Our eyes are so sensitive that it just takes a few photons to cause this nerve impulse. Now let's test your knowledge. Rank the following compounds in order of increasing stability. Remember, the more conjugation, the more stable a compound is. Now, using those same compounds, rank them in order of increasing lambda max. So if you were testing all four of these compounds using UV-Vis spectroscopy, what would their ranking be in order of increasing lambda max? Remember, the more conjugation, the higher the lambda max.